Hello, my name is Ben O'Sullivan. I'm the Materials Technology Team Manager here at Trelleborg Offshore, based in Skelmersdale, and today I'm going to be giving you an introduction into syntactic foams and how we use them here at Trelleborg. So as an agenda, we're going to firstly talk about the basics, so what is syntactic foam and what is it made from, and then we'll delve a little bit more into more detail in the chemistry of syntactic foams before talking about why is syntactic foam needed and what do we use it for here at Trelleborg Offshore. And then finally, we'll look at some of the key properties of syntactic foams and the things that we continually monitor here at Trelleborg to ensure quality control of all our products. So firstly, what is syntactic foam? Syntactic foam is a lightweight, high-strength material created by mixing hollow spheres with a resin matrix, and this creates a composite containing voids. The word syntactic is actually Greek and comes from the word syntax, and it means in scientific terms the combination of order, and this refers to the combination of hollow spheres within the resin matrix. The word foam refers to the cellular nature of the composite itself. So when we talk about syntactic foams, there's two main categories. There's pure syntactic foam and composite syntactic foam. So we'll firstly look at the pure syntactic foam. So this is a building block of the composite, and it's produced by combining hollow spheres with a polymer binder. Now these hollow spheres can be made from multiple materials such as ceramics, metals, but at Trelleborg we typically use glass, and these are called hollow glass microspheres, or HGMS. The polymer binder, also known as a resin matrix, holds these microspheres in place, and once the material is cured, we have a syntactic foam. So to look in a little more detail at these constituent parts, the hollow glass microspheres, or HGMS, is typically borosilicate glass bubbles, and these vary in diameter and particle size, but they're absolutely microscopic, typically below 120 microns. Depending on the depth rating of these hollow glass microspheres, the density changes drastically and can go from anything from 120 kilos per meter cubed up to 600 kilos per meter cubed. And even though they're very low in density, they display very high strengths, and this is critical in the end application and the use of syntactic foams. The polymer binder can vary drastically depending on the application too, and we typically use either thermoset polymers or sometimes thermoplastic polymers. When we use thermoset polymers, we use something like an epoxy anhydride resin matrix or an epoxy amine resin matrix, and sometimes for certain applications we also use polyurethanes. In terms of thermoplastic polymer systems, depending on the application, we can use a wax-based polymer system. And in combination, these hollow glass microspheres and the polymer binder create a syntactic foam which is low in density, high in strength, but also displays properties such as low thermal conductivity and high stiffness. Next, we move on to the composite syntactic foam. Now this is a secondary composite in which the syntactic foam is combined with larger hollow spheres, which we call macrospheres. So macrospheres introduce more air into the composite, and therefore they help create a lower density overall composite. And this is something that's critical in the end application. To look again in more detail at the macrospheres, typically we use two types of macrospheres at Trelleborg Offshore, and they depend on the application. We can use either of these things interchangeably. Thermoplastic macrospheres, these are injection molded macrospheres using a thermoplastic polymer, and they're reinforced with glass fiber to add strength. The benefits of these are due to the injection molded nature. They're very precise in shape and density, and therefore they're perfect for an application in which we have a tight density tolerance. However, due to the nature of the polymer used, they're limited to 100 degrees centigrade, and therefore this needs to be kept in mind when designing a system or processing a system. Secondly, we use thermoset macrospheres, and these are manufactured in-house at Trelleborg Offshore UK in Skelmersdale, and they use fiber reinforced epoxy technology. This is a manufacturing process that we've used for years here at Trelleborg, and it's based on coating a polystyrene core with fibre and resin. The more coats you add, the higher density and higher strength the sphere becomes. We use different types of fibre depending on the application to meet different density requirements. And these spheres can range from anything from 5 mm in diameter up to 40 mm in diameter. So next, we'll look a little bit in more detail at the syntactic foam chemistry. So you've heard me mention both thermoplastic and thermoset polymers in the previous slides. So to look in a little more detail at what that exactly means, most of the time here at Trelleborg we use thermosets, but it's also important to note that we sometimes also use thermoplastics depending on the application. So a thermoset polymer is a polymer in which you have two or more components and they're reacted together and they create permanent bonds. Now, the creation of these permanent bonds means that the process is irreversible and those bonds cannot be broken easily, and therefore you have a cross-linked matrix. A thermoplastic polymer does not involve any cross-linking, and therefore you have a polymer backbone which can simply be remelted and remolded multiple times. So look in more detail at the thermoset chemistry, which is typically what we use here at Trelleborg. We would use something like an epoxy resin with a hardener, either an anhydride or an amine, and this forms a cross-linked matrix of thermosetting polymer. In combination with the glass microspheres, they're encapsulated within this resin matrix to improve the strength and give an overall low density, high strength material. Now, we use both amine and anhydride hardeners, and they have different benefits depending on which type you use. An amine hardener, for example, is a self-curing process, but has a limited pot life and therefore can pose processing difficulties. Whereas an anhydride hardener requires heating and an accelerator, but has a much longer pot life, and it means processing can be longer and therefore is suitable for larger parts typically. So why is syntactic foam needed, and what do we use it for here at Trelleborg? So there are many applications worldwide in which syntactic foam is used, so from aerospace to defence to thermal insulation, tooling board in Formula One cars. It's a very versatile product and therefore it's suitable for many applications. However, at Trelleborg Offshore in Skelmersdale, we use it for one main reason, and that reason is buoyancy. So syntactic foam and composite syntactic foam help reduce the weight of heavy subsea structures by providing buoyancy, or upthrust as is sometimes known as. Not only does it provide upthrust, but depending on where the buoyancy is provided, it holds certain structures subsea in the correct configuration. This is why it's extremely important that the syntactic foam has a high strength to weight ratio. The lower the density of the foam means that more upthrust is provided, and the higher the strength means that the deeper the syntactic foam can be used. So the ultimate goal of syntactic foam is to have as high a strength to weight ratio as is possible. In terms of the products we use here at Trelleborg Offshore, there are two main ones amongst many. So the first one is the NordDBM, or Distributed Buoyancy Module. So these modules hold subsea pipelines in certain configurations by providing buoyancy to the pipe. They're held in place by a clamp and typically contain composite syntactic foam using thermoset or thermoplastic microspheres, as we discussed earlier. These products typically have a longer design life, 25 years plus, but that can go up to 40, 50 years depending on the project. The other type of products we make, which is similar in concept but has a shorter design life, is the Magni DRBM, or Drill Riser Buoyancy Module. These are modules that are strapped to heavy drill risers that are deployed from a drill strip in the extraction of oil. These are typically made from the similar kind of composite syntactic foams, but use a glass reinforced epoxy skin to provide extra structural strength. So finally, we're going to talk about the key properties of syntactic foam. Syntactic foam displays many useful properties, and depending on the application, some are more key than others. For example, in thermal insulation applications, a lower thermal conductivity is the most important property. In a high temperature environment, things like the glass transition temperature and the thermal expansion coefficient are very important. However, in subsea applications, there are four key properties. Those properties are hydrostatic strength, so what pressure can the material resist without collapsing or crushing? Bulk modulus, so how stiff is the material? How much will it compress at a pressure subsea? Water absorption, how much water will ingress into the foam over the design life? And hydrostatic creep. So all polymers typically creep under load. So how much is this syntactic foam going to creep over the design life? So these four key properties can be measured typically in two specific tests. So they're known as the hydrostatic crush pressure test, or the HCP test, and the instrumented buoyancy loss test, or the IBL test. Firstly, we'll take a look at the HCP test. This is a test in which a representative sample or full-scale module is subjected to an increasing hydrostatic pressure until failure. This gives us information on the ultimate instantaneous strength of the sample. However, it doesn't give us any long-term performance indication. The HCP of the material also allows us to give a factor of safety on the system. And in industry, this is typically 1.5 times the design pressure of the system. For example, a system that's going to be used at 2,000 meters below the sea needs to have a hydrostatic crush pressure of greater than 3,000 meters pressure. The fail point of the HCP test can be defined in two ways. The first way is the ultimate collapse of the sample, so the point at which the sample physically collapses or crushes. And the second is the point at which 5% of the buoyancy of the sample has been lost. Now, we define the HCP as the lower pressure of these two different criteria. And as you can see on the sample on the screen here, criteria 2 is met before criteria 1, and therefore the HCP would be the pressure of the green line. Next, we look at the IBL test, or the instrumented buoyancy loss test, and this gives us more confidence in the long-term performance of the composite syntactic foam. This test is a long-term test, and again is done on a sample that's representative or a full-scale sample, and it's subjected to pressure for anything from 24 to 96 to sometimes 1,400 hours, depending on the customer and the industry specifications. The buoyancy loss is monitored continuously throughout the test, either by a load cell or an LVDT, and this can measure the weight gain of the sample and therefore the buoyancy loss of the sample. The long-term properties of the material can be extrapolated through a logarithmic trend, and that allows us to understand the buoyancy loss of the material at the end of the service life. From a typical IBL trace, there are three characteristic parts. Number one is the initial buoyancy loss, and this is seen during the ramp up to pressure and tells us about the elastic properties of the material. From this, we can understand the bulk modulus of the material or the stiffness of the material. Ideally, we want the higher bulk modulus as possible, and therefore the sample compresses less and there's less buoyancy loss during the ramp. Portion 2 is the long-term buoyancy loss of the sample. This is made up of two properties, the water absorption and the creep. As the sample is subjected to constant pressure, water finds its way into the materials and increases the weight of the sample. This reduces the buoyancy over time. Likewise, all polymer materials creep under load, and as the sample is again subjected to long-term load, it will slowly contract in size, and again the buoyancy will reduce. The third component of this graph is the extrapolation to design life. From portion 2, we can extrapolate onwards to the end of design life and understand the buoyancy loss at the end of the service. As we can see here, plotting on a logarithmic scale allows for extrapolation of the buoyancy loss to design life. This is typically 25 years or 219,000 hours. And typically in industry, this needs to be less than 5% for the project requirements. So finally, to summarise, today we discussed syntactic foam and what it's made from, and that it's a mixture of air bubbles and a matrix to form a syntactic foam. We then include larger max spheres to decrease the density further, and this is called a composite syntactic foam. We looked at what we use it for, so syntactic foam provides buoyancy to heavy subsea structures by typically having a high strength to weight ratio. And then we talked about key properties of syntactic foam here at Trelleborg Offshore, and those are things such as a high bulk modulus, high hydrostatic strength, low hydrostatic creep, and low water absorption. And then finally talked about the testing we do at Trelleborg Offshore to ensure product quality. And these are tests such as short-term tests, like a HCP or hydrostatic crush pressure test, and then also long-term tests, such as an IPL test to assess buoyancy loss at the end of the service life. Thank you very much for listening today. I hope you've enjoyed an introduction to syntactic foams. And if you have any further questions, please don't hesitate to contact us. Thank you.